All right. Hello and welcome to the final 3D30 for the year. Today, happy holidays has come early because we're going to be talking about something that we've never really opened the curtain on as widely as we'll do today. So, this is a first for us. We are going to be exploring Velo3D's cutting edge non contact recoder. So, get ready. This will be an exciting 30 minutes. 3D30 is Velo3D's LinkedIn Live and YouTube Live channel. If you're new to this channel, we host this about every 2 weeks. And what we like to do is kind of keep on that schedule, but with trade shows and the holiday season, obviously it's a little up in the air. So make sure that you follow Velo3D on LinkedIn to get the latest show schedule, and then you won't miss anything, especially when we talk about topics like this. So, people always ask us at trade shows, we've had a couple of these, how do we do what nobody else can do? How are we printing parts that other companies struggle with? What's the secret? And one of the big secrets is what we'll talk about today. It's this non-contact recoder. I'm not going to get into too many details. We're going to leave that for our guest. But you're absolutely in luck today because we're bringing on, for the second time, there he is. There's Michael Harsh. Michael, welcome to the show. He's our technical sales engineer for the EMEA region. And he is a wealth of knowledge, both at Velo and just kind of industry in general. And so we're going to be diving into this technology with Michael today, and he's going to give us some insights. Just as a reminder, this is a live show. We love the questions. We want to host these live. That's why we kind of get on the cameras and get the mics out and do these for real. If you do submit a question, there can be a slight delay. So just, keep that in mind. We do keep our eye on the red dot. And when that comes on, we try and get to your question as soon as we can. But logistics are being what they are. So today we've got Mike and Mike on the mic. I always like saying that. So Michael, what's new? How have you been?
Yeah, pretty busy. I mean, Formnext, people maybe remember me from that show if you've attended or if you've seen the last 3D30. So we were super busy. Now it's all about following up and getting in touch with our future customers. So really exciting time to have all of these conversations.
Awesome. And I have to ask, how many times did you get asked, what's the secret behind Velo, or how do you guys do these parts that nobody else can do?
I think it's impossible to count that, but at least 50 to 100 times per day without exaggerating.
Yeah, I think it has got to be the most common question. And this is a key part of it. So before we get too far into the details, I think we're going to back up a little bit. We're participating in a technology called laser powder bed fusion, building parts layer by layer. Can you kind of walk us through a little bit of that?
Yeah, always a good idea to establish some sort of knowledge base in the beginning. So laser powder bed fusion is one of the many additive manufacturing or 3D printing processes common or used in the industries. And laser powder bed fusion is a process where we use metal powder, so plasma atomized or gas atomized powder particles, size around, let's say, 10 to 60 micron, depending on the material, depending on the process. And what we are doing is we lay this powder out in a thin layer, and this is where the Recoater actually comes into play. And when we've spread out that powder, and the target here is to do it very uniformly, homogeneously, so consistent layer thickness, consistent packing density in the powder bed, we will then start to basically create a laser weld. So we have one or more, depending on the manufacturer, depending on the machine, light source or laser source that is numerically controlled, and will then create one slice or one cross-section of the part, or scan one cross-section of the part that we want to build. And when we've done that in one layer, just to give you an idea, layer thicknesses in the industry are typically between 20 to 100, 150 microns. We will lower the build plate and repeat the process. So it's always lay down a layer of powder, laze it, melt it, wait till it's solidified, or it solidifies immediately actually, and then repeat the process. And if you do that enough times, you are able to create a full part.
So I've actually brought one of my little show parts here. So basically, none of this exists. You've got powder, like a sand almost. It's really
Mhm.
fine. You mentioned kind of the size 10 to 60 microns. It's like a human hair type of thickness there. And then you're just going to laze, and then this is going to keep going down and down and down and down, and then this gets buried under all that powder eventually.
Yes, exactly. Like in the end, when the part is finished, you have to remove the excessive powder that has not been melted around the part, and then you can take your part out and do post-processing or get it to the finished state that you need in your final application.
And we've got a short video here. We actually can't do audio while the videos are playing on our platform, but this will give you an idea. It's a rendering, and it's just going to show kind of that lasing powder, and you'll see this. It is the recoater, but it looks like a giant mirror is sliding out to you and back. So take a look at this real quick, and this might give you a good visual.
Yeah, that's pretty much it. And I think, soon we'll talk more about some of the intricacies of the process related to the hardware on the machine.
Yep. And for some of the AM savvy people in the audience, I just noticed this myself. What was wrong with that video? So you can go ahead and put in a chat thing if you see it. We did something to the video that modified it a little bit, and I just realized it. But hey, it could be a fun trivia. So we got some comments here. Let's see. Oh, okay, that's from Amir. Yeah, so please leave your comments here. We're curious to see. But based on that video, there was something kind of curious about it. But we'll get into that. So yeah, so we have this big mirror, and we're calling that the recoder. So what is that? What is that functionally doing?
Yeah, I mean, I touched on this a little bit. So what you want to do is you want to create a powder bed that is of high quality. And what does high quality mean in that context? It is that across the entire build platform, you have homogeneous or uniform layer thickness. So just to give you an idea, in our standard process, this would mean around 50 micron. Of course, there's some tolerance, but we want to keep this as uniform as possible. And also, there's different approaches here in the industry to also take care of the packing density. So if you drop the powder on the table or on the build plate, depending which type of recoating system you use, you can get different qualities of powder bed in the end.
And you kind of mentioned different types, but what types are out there? Obviously not everybody has a non-contact recoder because we're talking about that as something unique.
Yes, I would say most of, if you look at the different manufacturers or systems that are out there, typically for the recoating, it's a simple blade. So this can either be from metal, carbide, ceramics, or you can also have flexible type of blades made from some sort of rubber or plastic. And finally, there's also an approach where people use rollers.
Okay. And so you've got these different approaches. What are some maybe pros and cons behind each of these, and why would an
Yeah,
engineer decide one or the other?
yeah. I mean, I would say it really depends what you are targeting to do, but all of the recoater systems that are out there have one thing in common, and that is really a very small or minimum clearance. It's actually the clearance that you want your working layer to be. So 50 micron clearance, and the recoater is dragged across the powder bed. And this can potentially be problematic, especially when you're going to more difficult geometries. We can talk about this in a little bit, but there's always a risk of collision or deforming the part, deflecting the part, exerting shearing forces on the part and the powder bed. And this can be very risky to the process, and in the end decrease the robustness or the repeatability of your process. So just to maybe highlight a little bit the difference between flexible and non-flexible recoater systems. So a ceramic blade, of course, will be very good at making a good smooth powder layer. The problem is, however, if that blade ever gets in touch with the part and the recoating blade or lip is not flexible, it can damage the part, especially in overhanging areas or high aspect ratio features. On the other hand, if you use a flexible recoating system like a rubber blade or plastic lip, that may not damage your part or warp your part, but it will wear out the recoating blade. So the risk is, if in that case this flexible soft material of the recoater comes in touch with the part, you're actually damaging the recoater blade and compromising all other layers, because there may be some wear and tear on that part.
So whatever pattern is cut into that recoater blade, you're basically recoating every single layer with that pattern, it sounds like.
Exactly. Yeah.
Yeah. No. Okay. So it sounds like there's some limitations to the existing technologies out there. Is there always a solution, or or do you just get stuck sometimes and you're not able to print parts, or what do you do?
There are different. I don't really think there are full solutions in many cases. It's more of working around the problem. So, one thing is, of course, changing the design of your part in the end to limit the amounts of the angle of overhang that you can do, or limit the thickness or aspect ratio of features that you can build. It can also mean that there's extensive process optimization for a particular region or part of your geometry, which is time consuming, takes a lot of effort, takes a lot of time. So in the end, yes, you can work around that, but it's usually a compromise or a sacrifice of some sort. And in the end, if you cannot change the design and you don't have time to do a lot of process optimization on your scanning side, it's support structure that people fall back onto. And support structure is fine if you can remove it, but if you cannot, the part is really not usable or not printable in the end. So I think this is where Velo is really providing a different approach, where I would be inclined to call it a true solution that is repeatable, robust, and
So if you don't want to compromise on your design, which I assume that's going to be a lot of designers who don't want to, like, if you're making a heat exchange and you say, oh, well, your wall has to be thicker, you can't have this aspect ratio, that kind of takes you down a channel that's maybe not the most attractive. So
yes,
there's good news though, right? So we have a non-contact coater, non-contact recoater. So talk to us about this.
Yeah. So the contact-free recoater that we have is a completely different approach. So in one recoating motion, what we are doing, so when the recoater is traveling, in our case, from the front to the back into its standby position, 3 operations are being carried out. So first of all, we have like a dispenser on the recoater, and that dispenser firstly will lay down a very thick layer of powder. Exactly, yeah. So this would be now the component that you see here on the left. So the recoater is traveling from left to right here, and first the dispenser is laying down around 2 millimeters of powder. And then we actually do have a blade on our system. This is the little triangle drawn here in the middle. But the key point here is that this blade does not have a small clearance. So this blade is not at a distance of 50 microns, but rather at a 1 millimeter distance. And what that blade does is, creating a uniform layer. And now the most important part, and I think this is the one that we've been very secretive about in the past, but the last component here is actually a vacuum unit. So it's a long nozzle, and that nozzle will remove the uniform, the bladed layer from 1 millimeter down to 50 microns. So that sounds awfully complex, but when we talk about this more and show some examples here, this is really a huge step towards solving the inherent process issue of laser powder bed fusion.
So what kind of advantages do you get? I mean, it's interesting. You kind of see that it's just floating above there.
Yes,
There's no physical contact. And here we took our logo. Obviously, you're not printing a bunch of V's all the time,
yeah,
but you could imagine this part protruding out of the powder bed, and yet there's no risk that you're going to damage the recoater or the part in this case.
yeah, exactly. So maybe we'll step back a little bit more and talk more about when issues happen in laser powder bed fusion, or when they are more likely to happen. So imagine you're building just a solid block of material, with straight walls. In that case, you usually don't see problems. It's very easy to control your process and to know what is happening. And that has to do, or partly has to do, with the amount of residual stress and that you input into the part by the high thermal gradient when the melt pool is solidifying, and the bending stiffness of the part. So it starts to get complicated. Maybe you can bring up that picture one
Yep.
more time. When we start going into these low angle areas. So in that case, there's the schematic of an arch, which is a good example. So as soon as you start building into that low angle overhang, the bending stiffness of the geometry is relatively low, or getting lower and lower depending how low the low angle is. And the residual stress in the part will then lead to warpage, as pictured in the second picture from the left, where the geometry wants to warp upwards or protrude through the powder bed. And imagine if you just have 50 microns of clearance here, and as soon as the protrusion is higher than 50 microns, you are colliding with that geometry. And this is then a big problem. It can either damage the part, break off the part, or wear out your recoater blade. And usually, this is a problem. It can be a catastrophic non-recoverable build failure. And this is where it's a big benefit of having a higher clearance on that part. And again, this ties into like one of the puzzle pieces why we can do these low angle overhangs with less or even no support compared to other systems is if we can allow for some protrusion, or to be honest, in some cases, really use that to our advantage when we combine it with some of our special scanning strategies, we can, not build that arch with a lot of supports, or in that case, the real name should be anchors, because what these supports here do is just increase the bending stiffness of that overhang. We can get around that and build that arch without support.
And
So
you
that would
mentioned
be,
that.
yeah.
I was just saying, you mentioned it. It's like one piece of the puzzle. You mentioned some scanning strategies. I do notice, like on the image here on the far right, like it doesn't look like it's doing that deformation. So there's more going on than just the recoater. And you kind of hinted at it. Can you talk a little bit
Yes,
more about what that other piece is?
yes, of course. I mean, I cannot really explain exactly what
Hmm.
we are doing, because this is really, yeah, one of our main IP points. But if you have a good preprint or slicing software and a database of processing parameters that are adjusted to different geometries, you can, yeah, on the one hand, limit the amount of protrusion that happens due to the scanning strategy, but also be tolerant to, yeah, just the physics and the protrusion that you cannot get around with. And this is kind of the game that we are playing here.
Yeah, so it's pretty powerful combination. I know we kind of mentioned trade shows at the beginning. This is one of the most powerful parts that we take to the trade shows. Can you talk a little bit about how we're making this chainmail and give people an example? This is
Yeah,
sort of
so this,
non-contact recoder at work at its best, I think.
yes, exactly. So this really highlights another advantage of our system. So imagine a stable process where you are actually not, even if you had a standard recoater, but your process is just fine. But even on a standard recoat, um, there are shearing forces being exerted by the recoater blade, yeah, onto the part. And in a case like this chain mail is
Hmm.
super delicate, and it's not connected to the build plate by any supports. So even the slightest amount of shearing forces would actually move these little chain links out of place and, yeah, not make this printable. So the chainmail is really pushing it to the limit. Where this really applies to on actual applications, I would say, is again these really high aspect ratio features. So imagine a freestanding 300 micron wall that we can just build forever because the shearing forces are near zero, and we will not deflect that part ever. So that's really a big advantage. And actually, there's another thing that I want to highlight here. So, a big topic is if you have these high aspect ratio features on legacy LPBF systems, you usually have to worry about how you orient them relative to the recoating direction. So, imagine you're just a vertical wall. You would always be taught to kind of orient that not parallel to the recoater, but perpendicular. So the deflection or the shearing forces will not bend the wall. In our case, it doesn't really matter in which way we orient the part, because, yeah, the shearing forces will not do any damage or any harm.
Yeah, it's very, very impressive, the capability. Um, but just sort of thinking about it, my personal experience with a vacuum is like I'm going to use it. It's either all or nothing, right? I vacuum the floor. It's either all gone. I don't leave. I don't remove and leave only 50 microns of dust behind. So, like, how is this controlled, and how are you verifying that this did what it was supposed to do?
Yeah, as some people might know, with regards to process monitoring or the amount of metrology we have on the machine, we also take a lot of care about, yeah, what we call qualifying our powder bed, or making sure the quality of the powder bed is high. And this is one of the auto calibration routines that we can run before a process. And what we do here is actually we are using a structured light projector and a high resolution camera with some image processing, where we, yeah, measure the quality of the powder bed. And we do that in three steps. So first of all, we want to make sure that the dispensed amount, so this is what the first thing that happens during the recoat, is correct. So that we are laying down the correct amount of powder. And what we're doing, yeah, we're doing like a third of a recoat, just laying down the powder and then taking an image with of that that structured light projection, and we can tell this is the amount of powder that we have laid down. And we have a tolerance here. For each material, it's individual, but we can adjust this amount so, yeah, that we can already make sure the dispensed amount is correct. Then the next step is, of course, to see how the bladed amount behaves. So doing 2/3 of a recoat, dispensing and blading, taking the same height mapper image again, adjusting the blade if necessary to have a correct homogenized bladed powder bed, and then finally doing a full recoat, doing the procedure again, height mapper image, and adjusting the vacuum head if necessary to also dial in the vacuumed amount. And this is actually, it's not something that the operator has to do a lot of manual labor. It's a routine that we run on the machine. It does the powder bed qualification, and it will tell you, yes, powder bed quality is good or not good.
Yeah, that's pretty amazing. So every step of the process being validated before you're running, or weekly, or on a routine
Exactly.
basis. Yeah.
And this is, yeah,
Oh, go ahead.
this
Go
is
ahead.
this is not just something that we do as a means of calibration and then we trust that it will be fine. We are actually doing these structured light height mapper images every layer. So after every recoat, we can tell, is the powder bed quality still okay? And we also do that after the part has been laced, which gives us an indication if there are protrusions or potentially catastrophic protrusions, which can happen. I mean, if the support structure is just too delicate somewhere underneath, or you have a protrusion that is higher than the clearance of the recoater, the machine will actually avoid a crash. And the cool thing is, when your part is done, you have a whole history of recoated and laced height mapper images that will give you an indication if the process was executed correctly.
And it's not just an image. You mentioned it. It's actual, like a topographical map almost type of thing, where you're seeing
Exactly. Yeah,
these patterns.
kind of like on a map, topographical map with mountains and valleys. This is what we do with the powder bed. So we can really, using the high resolution image, using the image processing of the structured light scan, we can get a lot of information. Like even if maybe the flowability of the powder has degraded, or if there's some other issues, we can have very high confidence that the powder bed is okay. And if we have that, that's half of the deal already for making a good part.
Yeah, that's pretty. So every layer validating
Yes,
the powder bed. That's
yes,
really powerful. So you kind of mentioned some reflowability. What are the implications to the rest of the system? I mean, this vacuum powder has to go somewhere.
yeah.
What does this mean to the architecture of the system that makes it different?
Yeah. So we really have a closed loop system, everything under inert gas and connected to an ultrasonic sieve and the material tank. So everything that is extracted or vacuumed from the chamber will run through the ultrasonic sieve under inert gas atmosphere back into the material tank. And so we're always making sure that the powder that goes out from the hopper or is being resupplied from the material tank to the recoater and the build chamber is okay. So everything is controlled in a closed system.
Okay, so the powder is fully recyclable. Then it just kind of keeps.
Yes,
Okay,
exactly.
well, that's pretty awesome. We are up on 30 minutes. I noticed the tag. The time just flew by today.
Yeah.
But if you do have any questions, please send them in now, because we're kind of up on time, and we'll try to get to them maybe live. But if we don't see it in time, we'll get to it in the chat. So feel free. This will be an open discussion. You can kind of leave a comment at any time. We'll be monitoring the chat and the comments that come in through LinkedIn and through YouTube, and we'll get back to you kind of in that channel. But I did want to, Michael, give you a second. Do you have any final thoughts or any things to sort of sum up your experience being at Velo3D, having access to technology like this, and
Well,
specifically non-contact recoder?
well, in my pre-Velo3D life, I've worked with different LPBF systems, so I know what the problems were with regards to the recoder. And I really have to, repeat myself here. I think what Velo3D offers with the contact-free recorder is a true solution, a solution that is repeatable, that can use standardized, validated processing parameters. You don't have to tweak, you don't have to modify or optimize your scanning strategies just to do a part. And to me, that's a true solution, which makes the whole thing or the whole process also really scalable and robust.
Awesome.
And
Well,
maybe another thing, I feel like maybe we need to do a follow-up or an add-on to this sometime next year, because we are not at the end yet. We know we have a good recoding system, and now we really have some great solutions or great optimizations in the pocket that will make this even more incredible.
awesome. Well, thank you very much, Michael. Great session today. Anyone in the audience, if you're interested in learning more about the non-contact recoder technology, Michael did write a blog, and there's a little bit more information available on the blog. So, take the time. We'll put a link in the chat, and please feel free to click on that and read and learn more. We'd love to see you on our channel. And with that, I think we're going to sign off, and I'll leave this blog up there so people can click it and download it.